All right, so let's get it started here. So, does anybody have any questions for me? Okay, so I just want to make a quick announcement about the final exam. As we know, the next week will be the last week in the semester. So I'm pretty sure that we will be finishing the syllabus by the end of this week. So by the Friday lecture, I think this will be maybe our last lecture, depends on how it goes during this week. And we could have the final exam at any time during the next week. So I didn't set up the time yet, but it could be Monday, it could be Wednesday. It depends. So actually, I might do it by the mid of the week, so I can give you guys some time to revise the content. But I will keep you posted through the announcement. So just keep eye on the announcement so that you will be aware of the exact time of the final exam. But I'm pretty sure it's either the Monday or Wednesday, and 70% Wednesday and 30% Monday. Okay, so let's continue what we started last time. So we were in a chapter 17, and we are done with the translation motion and fixed axis rotation, and we were about to start the general plane motion. So for the general plane motion, it's the same equations, but we have all the equations, we have equation in X, equation in Y, and a moment equation. And for the moment equation, if you are taking the moment about the CG of the body, so it will be the mass moment of inertia about the CG multiplied by alpha. But if you are taking the moment about any random point B on the body, so you will have to add another term, which is the cross product of the RG with respect to B, something like that. So this is RG with respect to B, and multiplied by the mass and acceleration at the center of mass. So let's assume that this body has an MAX is in this direction. Okay, so MAX like this, and there is no MAY, so we only have this. So we multiply this by that, and then get the moment at B. And if you are taking the moment about the instantaneous center of zero velocity, which is a special case, you can get the mass moment of inertia about the instantaneous center of zero velocity and multiply it by the alpha of the body. So if this, as we know, this is the instantaneous center of zero velocity. So you will get I at G and then transfer it to here by adding the mass multiplied by D square. Then you will get the I at the instantaneous center of zero velocity and then multiply it by alpha, which will be much easier than doing a cross product and get messed up with the sign and the cross product process overall. So let's solve an example on this application. So for this example, we have, it says that determine the angular acceleration of a spool, and it has this body. And actually, this spool is not that perfect circle because it has some much higher thickness at 0.2 meter, and it has a groove. So we cannot use the eye of the cylindrical disc or the plate, like the circular disc. So here's given in the problem that the spool has a mass of 8 kilogram and it's given the radius of gyration. So if you are given the mass and the radius of gyration, you can get the mass moment of inertia of the body. So the mass is equal to 8 kilogram and the radius of gyration is equal to 0.35 meter. So if you want to get I bar, it's equal to m k squared, so it will be 8 kilogram multiplied by 0.35, and this will be equal to 0.98 and we have kilogram meter square. So we got I bar. So this is how we get it. So this is the only given that we have, and the chord is negligible mass are wrapped around the inner hub and outer rim. Okay, so here we have a cable attached to a fixed roof, and there's a spool, and then you have a cable at different radius, and there's a force 70 Newton pull from this point. Okay, so let's determine the angular acceleration of the spool. Okay, and as I told you, if you want to solve any problem, so you will have to draw a free body diagram and a kinetic diagram. Okay, so for the free body diagram, we will put all the forces. So this spool has a weight, so I have weight going down, and I know that there's a cable here and cable there. So this cable at this point will have tension, which we don't know. And here, this cable is pulling with a force 70 Newton. So we put all the forces. And for the kinetic diagram, okay, so for this, I know that this spool will only allow to move in the Y direction because it will never move in the X direction because there is not any forces in the X direction. All the forces are in Y direction. So with force 70 Newton, and we have a weight, so we can calculate actually the weight. So the weight will be equal to 8 multiplied by 9.81, and this will be equal to 78.48 Newton. Okay, so the weight will be equal to 78.49 Newton. And here we can assume that this spool will be going up under this force, and we will have MAY, and we know that MAX will be 0 because there's not any forces in the X direction. And let's assume that this spool will be rotating in this direction, and this is the direction of alpha. So we will have here I bar alpha. So here I put all the accelerations, and here I put all the forces in the free body diagram, here and here. Okay, so the next is to write the Newtonian kinetics equation. So let's get our first equation, and you can start by anyone. You can start by the Y direction, or we'll start by the moment. It doesn't make any difference. But let's start by the sum of the moments about G, and this will be equal to I bar multiplied by alpha, which is the equation that we have here. Okay, as I told you, we can get this part, the left-hand side, we can get it from the free body diagram, and the right-hand side, we will get it from the kinetic diagram, but we need to define our positive. So let's assume our positive direction is in this direction. Okay, and this is our G. So let's get the moment about this point. If I get the moment about this point, I will cancel the W because the arm of the weight will be 0. So we will only have the 70 and we will only have the tension. So the 70 kilonewton from the right-hand rule will exert negative moment. So it will be negative 70, negative with respect to the sign I decided. So with the arm of 0.2 meter, because the small radius is 0.2, and the tension will be having a positive moment from the right-hand rule. So this will be T multiplied by 0.5 meter. And this will be equal to I bar, which we got it here, 0.98, multiplied by alpha, which we don't know. So this equation has two unknowns, T and alpha. Okay, so let's keep it here, equation 1. And let's get to the second equation. But before I get to the second equation, I want to mention that you can get the moment about the instantaneous center of zero velocity. We know that this is an instantaneous center of zero velocity, and the sum of the moment about this center will be equal to the I about this center multiplied by alpha. But you will have to do an extra step. You will have to multiply the mass and transfer the mass from the G to the instantaneous center by multiplying m by 0.5 square. So you will do an extra step, so which is not needed. And actually you will have to identify some dimension. And actually you can do this by I bar multiplied by alpha plus rg with respect to the instantaneous center of zero velocity crossed by ma, which will be much more longer. So the moment about g here is perfect and much more easier. With this, let's move to the second equation of the Newtonian kinetics. It will be sum of Fy equal to the mass multiplied by MAY, like this. And let's determine our positive is going up. Okay, so let's see what is the forces that is going up. We have the tension, we have the 70, so T plus 70 minus the weight, which will be 78.49 because it goes down, equal the mass. Oh, just like one last thing. Is this equation 1 is right? Did I miss any sign or anything is not right? Does anybody know if I missed something? I missed something actually, and I would like you to discover it. So checking the sign of the forces, we have negative 70 is going up. Sorry, negative 70 is making negative moment like this. And T is making positive moment because this is the direction. But here, we assume that alpha is in this direction. And we assume our positive is in the other direction. So I will have to have negative here. Okay, so that's was the mistake here. So let's move to Fy. And actually, let's check the signs again. So we have T and 70 going up and weight is going down with negative sign. And let's check the sign of MAY. So AY is assumed to go up and our positive is up. So our sign here will be positive. So it will be mass, which is, the mass is 8 kilogram multiplied by AY. And actually we can get AY as a function of alpha. So we know that if we have a body like this, and we need to get, and this is an instantaneous center, and we know that this body is moving this way, so this will be the A tangent, and it will be equal, which is A tangent, which is AY, will be equal alpha of the body crossed by RG with respect to the instantaneous center. It's this one. And we know R, and we know the direction. So the direction of this, so alpha, let's keep alpha like that, and we have R, it is something like this. So I know the direction is in the positive direction, and R is equal to 0.5. So this will be equal to 0.5 alpha. So I transferred AY to alpha. So here it will be equal to 8 multiplied by 0.5 alpha. And it has a positive, this has a positive direction because it's going up and our sign is going up. So right now, this is our second equation. And its function in T and alpha. So now we have two equations and two unknowns. So if you reconstruct this equation, it will be T minus 4 alpha will be equal to 8.48. And the second equation, it will be 0.5T. So this is the verse equation, 0.5T plus 0.98 alpha equal to 14. If you solve these equations, you're using your system equations in the calculator, you will find that T is equal to 21.58 Newton and alpha is equal to 3.28 radian per second square. So we got what is needed, which is the angular velocity. So does anybody have any questions? So my tip here is just like to keep eye on the signs, don't mess one, identify the sign, make sure that the assumed direction of the I bar alpha and the mass acceleration matches the sign convention that you have for the Newtonian equations. Okay, so actually let's solve another equation so we can make sure that another problem, so we can make sure that the concept is very clear. So here, example. Okay, so let's okay. So here, okay, so we have a letter or a piece of wood or whatever of a 4 feet length. So this length is 4 feet, and it makes an angle with the ground of 30 degree, and we have a wall that is inclined with 45 degree, like this, and this is a frictionless surface, so there is not any friction, and let's assume that this is point A and this is point P, and you are given that the weight of this body is 50 pounds and slides friction free if the rod is started at rest. So this rod is started at rest. Find the number A, find the alpha of this rod, and number B, find the reaction at A and B. So we need to find the reactions at these points. A and B, and number C, find the acceleration at the centroid. Okay, so actually you will just like recognize that this is a general rotation or a general plane motion, because if this body is going, if A is moving this way and B is moving this way, this body is making translation and rotation at the same time, such as the one from previous one. This body, when it goes up, it rotates, and actually G is could be moving from here to here, so it translate and rotate. So we will have to apply our Newtonian kinetics equation, but before this, let's draw a free body diagram and kinetic diagram. Okay, so we have this is not 45 degree. And let's assume that this is our body, something like that. And let's see what forces that we have on this body. So in the middle of this body, we will have the weight is going down, and there is not any moment or any external forces, but we have reactions. And as we know that the reaction or the normal force acting perpendicular to the surface. So the normal force or the reaction here, it will be normal to the surface. So we will have an A here, and here we will have an B, something like that. And if we want to know in some angles, so we know that this angle is 45 degree. This one will be also 45 degree. And so we know that 45, and we know that this is 30. Okay, so I want just like, so this angle will be, so let's see, yeah, this angle will be 30 as well. And We know that this is perpendicular to the surface. Okay, so let's make a perpendicular to this body. Okay, so this is 45, and this angle will be, yeah, this and this. Okay, so this angle is perpendicular. Okay, so here's 45, 30. So let's find this angle. Okay, so we will know, okay, let's extend this line like this. And this angle will be 45 degree. So we can find this angle. It's much bigger, but it should be 15 degree because this and this should be equal to 45. And we know that this NB is perpendicular to the surface. And we know that this angle should be 90 degrees, something like that. And this is 45, so this will be 45 as well. Let's make it in red. 45 as well. And we know that this angle is 45. And okay, yeah, much more confusing here. So if we want this and this, okay, so this will be a 45 degree with the vertical. So yeah, from this will be 45, and this will be 45. So this is 45 as well. Was this one? And we will have, okay, so yes, this angle should be 60 degree because this is 30 and we know that this is 45, so we will have this is at 15 and this is at 45, and this will be 15 as well. This one. So it just like need you to do some geometry to identify these angles, just like because we have a perpendicular to this and a perpendicular to this line. And we know this angle is 45 as this angle is 30. So you can actually identify the angle between the NB here and anyone with the like with the horizontal, with the incline and 45 and incline and 30. So just like need some focus to identify all of these. Okay, so we have the forces NB. Okay, let's actually clean all this mess. Just like right. So yep. And we will have NB and this what we need. Okay, so this is the three forces that we have here. And let's get to this is the free body diagram. And let's get the acceleration. So, okay, so this body should be like here moving, let's assume it will be moving this way, and this point is going down as soon as it moves. So let's assume that this is MAX and this is MAY, and it rotates this direction. So this is I bar alpha. And you should note that these points will be moving this way. This is the tangential direction, so this will be MA at A, and this is the M A at B. So this is how it moves, and this is actually the velocity VA will be in this direction, and the velocity VB will be in this direction. If you want to know the instantaneous center of zero velocity, you will draw a perpendicular to this surface and perpendicular to this surface, or not the surface to the velocity, and you will be able to find that this is the instantaneous center of zero velocity. And this line is not equal to this line because we have here an angle like 90 degree and here's 45 degrees. So just like make sure that you do the geometry right because we have different angles here. Okay, so if we started to construct our dynamics Newtonian equation, you will end up with NA unknown, because if you take the sum of the forces of Fy, NA will appear, and if you take the, and also NB will appear because it has components in the X and Y direction. And also the acceleration will appear here because this is our equations. The sum of Fx will be equal to Max bar, the sum of Fy will be equal to the May bar, and the sum of moment about G, it will be equal I bar multiplied by alpha. We don't know the Ax and we don't know the Ay, and also we don't know the alpha, and we and also NP and NA will show in the final forces. So it will end up with 5 unknowns in the equations. So we need to relate AX and AY, relate them together in terms of alpha, because if we know the alpha of this body, we can know the MA as a function of alpha and the MAB as a function of alpha, and also then we can get I bar with respect to alpha. So we need to get MA versed with respect to alpha and then relate the center here to this MA. Okay, so if we want to get the acceleration at point A here and relate A with P, so let's get A B equal to AA plus AB with respect to A, and all of these is vector components. So for AB, we know the direction because we know that it's going down, and we know that this angle is 45 degree. So this is AB, and it should have a component in this direction and a component in this direction, and this angle is 45 degree. So AB will equal to AB, and the X component is cosine 45, the I hat, and the Y component is in negative AB sine 45 in the J hat because it's going down. So we know the direction, but we don't know the magnitude. And this should be equal to the A at A, the acceleration at point A, and we know that A is going in the I hat direction, so it will be the magnitude of A, and it's in the positive I hat, plus AB with respect to A, so this will be equal to alpha of the body, and actually let's make it alpha, crossed by RB with respect to A. And actually that's what we can know this. So this is our body, and we know the angle here is 30 degree, and from here to here this is point A and this is point A, so B and A, so this is RP with respect to A. So RP with respect to A have a component in X and component in Y, and this will be equal to, so let's put alpha, and I assume the alpha is counterclockwise, so it will have a positive direction if you use your right hand rule. So we will have alpha in the K hat. This will be crossed by RB with respect to A. We know that this is 4 foot in length. So let's analyze the 4 foot in cosine and sine. So we will have -4 cosine 30 in the I hat direction, and then we have plus 4 sine 30 in the j hat direction. Okay, and then when we are done with the cross product, we will end up with one equation, and it has some components in the I hat direction and other component in the j hat direction. So we will have, this is the I hat. So yeah, just like I want to emphasize on this, the any vector component, if it's a 2D vector equation, it has I and j component, we can separate it into two equations, one in x and one in y. And if it's a 3D vector equation that has I, k, and j, so we can have three equations, one in the I and one in j and the other in the k direction. So in the I hat, we have AB cosine 45. What else? We have AA. Sorry, this is in the other A at A here. And let's see what we have in the I hat direction. If you multiply K hat by I hat, it will give you a component in the J direction. But K multiplied by J will give you -4 sine 30 multiplied by alpha in the I hat direction. So let's remove because we already have the I hat outside. And this is for the I hat. So for the J hat, we have -AB sine 45, and we have alpha. K multiplied by I will give you J, but we have negative here, so we'll have -4 cosine 30 multiplied by alpha. Okay, so based on this, we will able to get the acceleration at A and the acceleration at B as a function of alpha. So this is a 3 unknowns. So let's get AB first. From this equation, AB will be equal to 4.899 alpha. And then we can substitute by AB here to get the AA. The acceleration at A will be equal to 5.46 multiplied by alpha. Okay, so we get the acceleration at A and the acceleration at B in terms of alpha of the body. With this, let's move to the acceleration of the CG of the body here. This body MAX bar and MAY bar. So we can relate the CG of the body with A. So we can say, so this is the part one of the problem, and part 2 of the problem. And this part 2, we will get the acceleration A bar or AG with respect to A. AG with respect to A. We will relate the acceleration at the middle here with point A. To do this, it will be equal to AA plus the alpha of the body crossed by RG with respect to A. And here we can divide this in X and Y, so we will have A bar X plus A, and sorry, we can remove the vectors from up here and put the I hat plus AY bar in the J hat. This should be equal to AA, and we know that the acceleration at A, it has I hat direction, so AA in the I hat. And I choose A rather than B because B has two components and A will be much more easier to deal with. And plus alpha in the K hat crossed by RG with respect to A. So RG with respect to A, so this is G, and this is A, and this is RG with respect to A. It will have 2 feet lengths, and it has the same direction like this is 30, so we can get 2, and it should have negative, because this is negative I hat, so negative 2 cosine 30 I hat, and it has a positive sign in the j hat, so plus 2 sine 30 in the j hat direction. And we can do the same, get the I hat direction, and we have ax bar, because this is at the CG, will be equal to a at a. And if I multiply it k by j, it will give me negative 2 sine 30 multiplied by alpha. And in the j hat direction, we have ay bar. And if we multiply k by I, it will give j hat. And we have negative outside, so this will be negative 2 cosine 30 multiplied by alpha. So, and we have actually AA, the acceleration at A, as a function of alpha. So right now we will be able from these two equations get AX bar will be equal to 4.46 alpha of the body, and AY bar will be equal to negative 1.732 multiplied by alpha. And let's box them like this. So right now I know the acceleration at x and y in terms of alpha. So now I can use the kinematic equation, because I can substitute ax by alpha and ay by alpha, and here we have alpha. So we will have 3 equations and 3 unknowns, which will be alpha and np and na. So let's do part 3, which is Newtonian kinetics. And for part 3, let's start with the moment. So let's get the moment about G. And the moment about G, so, okay, let's have the forces NA, and I have weight, and this is perpendicular to the surface, NB. And I want the moment about this point. If I want a moment about this point, the best thing is to do for the weight will be canceled, because I'm taking the moment about G, and NA will be multiplied by the horizontal component, so multiplied by this. And for NB, I can make an X component and Y component and get the moment of the NBX and NBY, but this will take much more time, and the easiest way is to analyze the normal force 1 in the direction of the body, and 1 is perpendicular to the body. So the 1 in the direction of the body, this one will be canceled because it has an arm 0, and we will end up with this component. If you did some geometry like what we did from before, you will find that this angle is the perpendicular one, it's 15 degrees. And mg will be equal to I bar multiplied by alpha. So let's get the moment. So this is the free body diagram, and we need to get the moment about this point. So let's start by NA. So NA will multiply by, we know that this is 30 and this is 2, so this will be 2 cosine 30. And I assume that the positive direction is this way, and NA is in this direction. So this will be positive multiplied by 2 cosine 30. Let's get to NB component. So NB cosine theta, cosine 15. It makes negative moment, so it will be negative NB cosine 15. And this is the force. Let's multiply by the arm, and the arm is 2 because this is perpendicular to the body, so this will be equal to 2. And this should be equal to I bar, and I bar, so you will have to identify the axis of rotation of this body. So this body is something like that, and it's rotating about this point, about this axis. And if you find this axis from the dynamics equation sheet, you will find it's 1/12 ml square. So I bar will be 1/12, and the mass will be the weight divided by 32.2, and L square is 4 square multiplied by alpha. So we got our first equation. And actually, let's reduce this equation. So after you do this multiplications, it will be 1.732 NA minus 1.93 NB. And let's get the alpha. It will be negative when we move it on the other side, negative 2.07 alpha. All of this will be equal to 0. And this is our first equation. Let's get the second equation by taking the sum of the forces in the fx direction. And this will be equal to ma x bar. So the forces that we have in x, it will be the component of b. So right now we need to get the component of b in the x direction. So this is the component, and this component, we know that this is 45 degree. You will end up with that this angle will be also 45 as well. And you will have fx will be, let's assume that this is the positive direction, and we will have nb cosine 45, sorry, or cosine or sine, it doesn't make any difference. And the mass will be equal to, I think the mass is 50/32, and the ax, we assume the positive direction of the x here, which matches our positive direction. So it will be, and actually we get the ex, it's 4.46 alpha. 4.46 alpha, we already get it as a function of alpha, and this will give us an equation that has 0 NA, there's no NA in this equation, plus 0.707 NB minus 6.92 alpha. This is equal to 0. And this is equation number 2. So let's get the sum of the forces in the y direction. It will be MAY. And the forces in the y, we have the weights, we have a component, we have NA, and we have component from NB. So we will have NA, and let's assume the positive is going up, minus the weight, and the weight is 50 pounds. And we will have plus NB sine 45, and it's going up here, this one. And this should be equal to the mass 50/32.2 multiplied by AY, and AY, we got it here, equal to negative 1.732 alpha. Negative 1.732 alpha. And after you done, you will find that this is NA plus 0.707 NP and plus 2.67 alpha, and all of this is equal to 50 after you transfer this into the other side. And right now you will have a system of equations, 3 equations and 3 unknowns, so you can solve it as a matrix, so you can construct a matrix like this. And actually, I totally recommend to use your calculator. We will have 1.732 minus 1.93 and negative 2.07. And we will have NA, NP, alpha, and this is 0. And the second equation is 0.707 NP minus 6.92. And the third equation is 1.707, 2.67. This is 0 and this is 50. You can solve using any equation solver or using your calculator, so you can get the reaction NA, which will be equal to 27.9 pounds, and NP will be equal to 22.56 pounds. And the alpha, which is required in this problem, will be equal to 2.303 radian per second. I know it's a very long problem, but if you have a strategy, if you know how to do it, actually you might start by part 3, but you will end up with that you don't have some unknowns. So you will have to find a way to get these unknowns. And then to do this, you will have to relate everything, all the acceleration to alpha, because the acceleration at any point of this body is related to alpha. If you were able to construct an equation that can relate this acceleration to alphas, so you will be able to solve this problem. Does anybody have any question on this problem so far?
Yeah. What do the little bars above the letters stand for?
What was that?
What do the little bars above, like the I and the A's, mean?
Which I have a lot of charts here.
Oh,
mean-
sorry. The bars, like in the summation of fx equation, it's summation fx equals m times a bar x. What does the bar mean?
The bar mean the acceleration at the CG of the body. So we say a bar, that means if you have a body like this, so the CG, we either call it AG or A bar, either is the same. And if it's in X direction, so we mean A bar in the X and A bar in the Y. So it's the acceleration of the center of mass of the body, like this. So this will be A bar X and this A bar Y, the CG. And you can call it G, whatever you would like. And if it's not center of mass, so we call it with the letter at this point. So if this is A, so this will be A, and if this B, so this will be AB. Do you have any other questions?
Nope.
Okay. Right, so let's move to chapter 18 and make a brief introduction for this chapter. So chapter 18 is the rigid body, work, and energy. So it will be related to work. Okay, let's write rigid body, kinetics, work, and energy. Okay, so for the work and energy, actually, it's almost similar to the particles. So let's see how similar it is. So if we want to get the work exerted by a rigid body, let's see what we have here. Number one, work done by variable force. So the work done by a variable force, if you have, like, let's assume this is our body, and you were able to, at any point of this body, and there's a force here, F, that has an angle theta, and this body only making translation, something like that, came here, and this is F, is making an angle theta. So it's similar to the work done by a force on a particle. So UF is equal to the integration of F vector dot product by the dr vector, or it's the F cosine theta ds integrated over the mass of the motion. So this is the mass of the motion. So this is S. And this is how I do it. And if f is constant, is not variable, I can take it outside of the integration. So number 2, work done by a constant force it will be equal f cosine theta, and if the mass S integrate the mass S, it will be the length of the entire S. So I can remove the integration and do direct multiplication by F cosine theta multiplied by the S. And this is because the only component of this force that exerting work on this body should be in the direction of the path. And any perpendicular force will not be exerting any work. So this is the work done by a constant force. And let's get to the work done by the weight. Work done by weight, which is similar to the particles. If we have, like this is our datum, and we have our body at this, let's say that our body started at this location, and this is the final location, and this is the path that the body move on, like this. And we have our weight is going down, and our weight is going down. Whatever the path that the weight moved through, we only care about the delta y, the distance in the direction of the weight, which is the vertical distance. If this body is moving down, like coming from uphill to downhill, like let's assume this is a rock and this rock is moving downhill. So this body is exerting a positive, is doing a positive work. But if this body is moving up, like somebody's holding something and going up, so that means that it's a negative work. So if you are going down, so this will be positive. If you are going up, this will be negative. So you will have the work done by weight, it's equal to W multiplied by delta Y. Because W is always going down, and we have this as delta Y, and the sign depends if you are going down or going up. And the work done by a spring similar to the particles, the work done by a spring is always negative 0.5 K multiplied by S2 square minus S1 square. And the S is measured from the unstretched length. So let's assume that this is our body, and we have a spring here, and the spring is unstretched at this location. So this is our zero that we measure from, and this is how much initial stretch that we have, S1, and we did much more stretch to make this body come here. So this will be S2, so it will be negative half K S2 square minus S1 square, or you calculate the delta S and make it square, but I would rather use S2 minus S1 square. Delta S square. All right, so this is the work done by a spring, and let's see the one new thing that wasn't in the particles, which is the work done by a couple moment or any moment, like 5 work done by moment. If we have a body like this, and let's assume that this body has a moment like that, and this moment makes this body to rotate and make an angle theta like this. So the work done by this moment m is equal to the integration of m d theta from theta 1 to theta 2, and if the moment is constant, we can take it outside and m will be multiplied by theta 2 minus theta 1 delta theta, and this should be in radians. So this is the moment done by, and this is rational because this is the moment is about the angular motion. So if we have F, it will allow the body to make some distance. So multiply F by delta S. But if we have moment, so it will make the body rotate, and this body will be making delta theta. So M will be multiplied by delta theta. So this is the 5 type of forces that can do moment. So let's see what forces that doesn't exert any work. Number 6, forces that do not do work. As we know from the last time, that the weight of a body while it moves on a horizontal, okay, so actually let's make it clear like what we did in the so let's assume that we have our rigid body here and we have a normal force. So this rigid body is moving this way and the normal force is perpendicular, so the normal force will not be exerting any work because it's perpendicular to the motion direction. Similarly, if we have a wheel and the weight of this wheel is going down, the weight doesn't exert any work because this wheel is moving this way and the weight is going down. So the weight will not be exerting any work because it's perpendicular to the direction of the motion. And similarly, the normal reaction from the ground on the wheel will not exert any work. And also one new thing, this wheel has an alpha this way, and this alpha is moving this way, which will at some point will come here and there will be a friction this way. This friction doesn't exert any work even it's in the direction of motion. Why? Because this is an instantaneous center of zero velocity. Whenever we have velocity equal to 0 and there's any forces at this point, these forces will not exert any work because it's like you assume that you put some forces on this body and this body is not moving. It doesn't have any velocity at certain point. So that means that there's this work hasn't been transferred to a movement in this body. And that's what happened here. You have friction here, but this is always V equal to 0. So this means that the friction here doesn't exert any work. And one similar thing is that if you have a bar like this, and we have a bin here, and as we know, if there's a bin here, we will have a reaction in the X direction and reaction in Y direction. This reactions doesn't exert any work because the velocity here is equal to 0. This point will never move. So this reactions will not exert any work. It's something similar to this N, and this point is not moving, so the reactions will not exert any work. Just like make sure that you have in your problem, if you have a force perpendicular to the, actually let's write them here. We have only 1 minute, so let's put one reaction at bin, support. Number 2, weight of a body while it moves horizontally. And number 3, force perpendicular to the direction of motion. And number 4, F friction on a round body. And also the forces at the supports, reactions. So this is the cases that the forces doesn't exert any work on the body. So for the next lecture, I will be recording the next lecture like after a few minutes and post it as well as this lecture. And we will not be having lecture tomorrow because I will be attending a conference. So I will not be able to be live on Zoom tomorrow. So what we will do, just like recording 1 hour lectures, and you guys are welcome to watch the lecture anytime today or tomorrow or within the time of the regular time of the lecture. So whatever the best works for you. And actually the next lecture I will be continuing on the concept of work and energy. So does anybody have any questions? All right, so see you guys the day after tomorrow.
Thank you. See you Wednesday.
Thank you, guys.